Okay, so we're gonna get started. First of all, good morning, good afternoon, good evening, wherever you are. If you're just coming out of bed, thank you for tuning in. My name is Corey Oses, and we're gonna be talking about thermodynamics. I'm gonna highlight a module in AFLOW that calculates thermodynamic stability among a larger set of properties using the AFLOW-CHULL or CHULL module. Okay, so the primary question that we're going to be dealing with today is the question of whether a material will form. And so there's two limits within which we can discuss this. There's the thermodynamic limit, and then there's the kinetic limit. So material can be in either control. This picture illustrates the difference. So here we have a reaction plotted plotted with the different energies. So here we have the energy of, let me get my laser pointer up. I think it's a little easier to see. Here we have the energy of the reactants, okay? And here we have the energy of two possible products, product 1 and product 2. So if we're in thermodynamic control, if the system's in thermodynamic control, then product 2 will always be formed because it's simply lower in energy than product 1. Okay, but we know that there's also a reaction pathway that we have to consider. Okay, and so while product 1 is higher in energy, its pathway is actually lower in energy. Okay, so you can imagine that if the energy of the system were such that the energy is around here, we can control this with temperature. Then product 1 is always going to be formed because product 2 will never. There's not enough energy to go through the reaction pathway to achieve product 2. Okay, so this illustrates the difference between the two controls, but for this talk, we're just going to focus on thermodynamic control, but they're both important for realizing materials. Okay, so what is thermodynamic stability? The question here is, we have an alloy system, palladium, platinum, and we want to ask the question, will it stay in this form, or is it going to decompose into its pure components, pure palladium and pure platinum? Okay, you can think of this as kind of separating like oil and water or oil and vinegar. So that's the question. To answer that question, the mechanism that governs that, we're going to be talking about the Gibbs free energy, okay, because we're interested in controlling temperature and pressure. And so the Gibbs free energy, again, Stefano talked a bit about this in his keynote talk. Professor Criterion talked about this in his keynote talk. So this is governed by the Gibbs free energy, and there's two terms to the energy. There's H here, which is the enthalpy, and when you see H, I want you to think of the ordering term. Okay, so this is order, and then we have a second term here, and whenever you see, so this is entropy. Entropy, I want you to think of disorder. Okay, so entropy is going to drive disorder, and it's scaled by the temperature. Okay, so the higher the temperature, the bigger this term is. And so from the second law of thermodynamics, we know that to be in equilibrium, we have to minimize G, we have to minimize the energy, while also maximizing the entropy. Okay, they're the same thing in equilibrium. For this talk, we're just going to focus on the enthalpy term, okay, order. We're just going to focus on order. We're not going to think about disorder. Disorder was a big topic of the keynote talk earlier today, but right now we're just going to focus on enthalpy. So here we have a plot. I want you to think of just for now, think of this axis as energy. And we have compositional space down here. So we have the pure palladium concentration here, and then pure platinum. We have three systems that I've plotted. I have the pure palladium system, the pure platinum system, and then the mixed alloy system, 50-50 concentration, okay? So now I've drawn a tie line here at the top in green between the two pure components. And if I look at the distance between the tie line and the mixed component, you see that the mixed component is below the tie line, okay? It's lower in energy than the tie line, okay? So that very visually tells you that the mixed alloy system is more stable energetically than its pure components, okay? So it prefers to be in this phase than to decompose into these phases because it's lower visually. Okay, now remember, we're going to neglect entropy. So we're just talking about the enthalpy term of the Gibbs free energy. And now you may have noticed that I've zeroed out the energies of the pure components, okay? So if you run a VASP calculation on these systems, the pure phase systems, you're not gonna get exactly zero. But for the visualization here, I've zeroed out the energies with respect to the pure components, okay? So that is what's called the formation enthalpy. All right, so you can just, it's the enthalpy of any phase, subtracting off the compositional weighted energies of enthalpies of the pure components. Okay, it's very simple. Now, decomposition may not just only happen with the pure components, but there's many different reaction pathways that an alloy system may decompose. Okay, so it can decompose not only to the pure phases, but other phases as well, phases that span the compositional space. So, you know, here we have a 50-50 mixture of blue balls to white balls. Here we have a different ratio. We have more blue than white. Here we have the opposite. And we also have variants that are different arrangements of the atoms. Okay, so here we have these nice planes of white and blue in diagonal form. And here we have, you know, opposite blue, opposite white. So different arrangement of atoms. Okay, and so in this picture, you can imagine that we have 527 different variants. We've done the VASP calculations on these, and we've calculated the enthalpies for these systems. Okay. And so now we want to ask, what are the stable structures of this alloy system? So that is a question of what points in this plot will not phase separate into any other combination of points. Okay, so we have to look at all of the tie lines in the system. Okay, and so if we do that, we're doing an analysis, we're building a construction of the convex hull, okay? So very simply, the convex hull is the set of the outermost points of this plot. You can imagine taking a giant rubber band and wrapping it around the data, and the points that it's going to touch on are the most stable points in the convex hull, okay? So from this construction, anything that is not on the convex hull is going to decompose, okay? And so what is it going to decompose into? Well, you look at the point here, okay, so we have PD2, PT3. We have this point here. In order to figure out what it's going to decompose in, visually take your eyes and drop it down to the convex hull, okay? Now this facet here of the convex hull, which is defined by these 2 points, are going to be the 2 components with which it's going to decompose. Okay, so we can actually make a chemical reaction, we can balance it based on the chemistry, and that is given very visually just by this facet point here. Okay, so that's what it gives. Now, nicely enough, the distance, okay, so this actual distance here between this point and the facet, the vertical distance, also gives us the energy driving this reaction. Okay, so you can imagine if this distance is very large, maybe the point is up here, then the system's really going to want to tend toward the products and not so much the reactants. Okay, but this distance here is small. Okay, it's 3 MeV per atom. Now remember, keep in mind that these calculations were done at 0 temperature and 0 pressure. Okay, and so if we're interested in looking for materials at, say, room temperature and standard temperature and pressure, then we're not only going to want to look at the points that define the ground state systems, but also points nearby. Okay, so we might account for the thermal energy, or room temperature energy. So this is about 25 MeV. Okay, so you can think of this as kind of an error to our plot. Okay, so we're not only, the point is to say that if we're looking for points that are stable and should exist experimentally, then we shouldn't only just look at the ground state systems as defined by 0 temperature, 0 pressure, but also by those that are nearby, maybe to within 25 MeV or a little more. All right, some details about the algorithm. So we have the module that calculates this automatically is called AFLOW-CHULL or AFLOW-CHULL. And so when you're doing this analysis, you're going to be grabbing data from the AFLOW database. And you know, one of the analysis it does is an outlier detection and removal. Okay, so you might imagine that in a particular system there could exist an outlier. So this system might be one, it might be ill converged. Maybe it didn't relax enough, or it was run with a different set of parameters. Now, with the AFLOW database, it's heavily curated at the database level. We've done a good job of looking for outliers, for analyzing for whether all the systems are very relaxed. All of the systems are calculated with the same properties. And so it's going to be very difficult to find outliers, but if they do exist, it's going to remove it automatically. We also do an analysis of duplicate structures. So for those of you that are familiar with the ICSD database, you know that there exist many duplicates that are distinct entries. And so for all of the stable points, we actually do an analysis of which ones are equivalent structurally. And this is done with a module that was created by Dr. Hicks, who presented earlier, but he didn't talk about it this time. It's called XTOL Finder. And this is all integrated with an AFLOW, and this analysis is performed on the fly. Okay, so someone asked about ternary phase diagrams. Here we have an illustration of one. I've shown you illustrations of binaries, right? Palladium, platinum. Now we have a manganese, palladium, platinum system. Okay, and so it looks something, instead of having tie lines, we're going to have tie surfaces. Okay, so this is a three-dimensional plot. Here we're looking at it from the top. Okay, so where the colors dictate depth in terms of formation enthalpy. So we're going to go ahead and play with this visualization. So if everyone will go ahead and navigate to aflow.org/aflow-chull. We have the backup here if anyone is having trouble. aflowlib.duke.edu, search UI aflow-chull. So I'll give, well, actually, I'm going to navigate there with you. Okay, so 1 second. Everybody should be able to still see my screen. Okay, so we're gonna go to, so I'll type it in again just so that I'm at speed with everybody. Everyone go to aflow.org, and if you scroll down, you're gonna see we have a button for AFLOW-CHULL. Go ahead and click on it. Okay, and we're all, just so that everyone's on the same page, we're gonna go ahead and go to the same one. So type in silver, gold, cadmium. Okay, and hit submit. And it should pop up pretty quickly. Okay. Give it a second for anyone who's a little slower. All right, so here we have a visualization of the convex hull. So it's a three-dimensional thing. Okay, so it's a three-dimensional polytope is what it's called. Okay, so you can actually pan it up. So if you hold down on your mouse, you can pan around. You can also zoom in. Okay, so you can zoom in and actually take a look at how the surfaces are defined. Okay, so remember the surfaces are defined by triangles in this space. Okay, and so in the binary space they're defined by individual lines, and in this case in 3 dimensions defined by three compounds. Okay, so you can zoom in, you can rotate, take a look at all the surfaces. I'm going to click on a point, and you'll see that it's going to pop up here. Okay, and while we're here, I'm just going to go ahead and ask everyone to go to selected points. Click on this little eye icon on the top. Okay, so you'll see that there's 4 points here. Just click on the eye with this point, or any point selected. It doesn't have to be that one in particular, and then give it a second. And it's going to load up the information for that point. Okay, so we have a compound name here. Okay. We have the AUID, which is the unique identifier for the AFLOW database. We can see here that it's not a ground state point. Okay, so it's going to decompose. We have some information from the database. We have the prototype name, designation. We have the lattice type, the space group, the energy of the system, the density, the formation enthalpy. We have the distance to the hull. And then we even have some other properties. Stefano talked about this morning the N+1. I'll talk about what the stability criterion is in a few slides, when we get back to the slides. But this is the N+1 enthalpy gain that Professor Cruderola was talking about earlier. So if we click on more info, we're going to get a loaded page that gives us all of the information calculated by AFLOW. Okay, so we get a nice individual page for that compound. We're going to get the picture here of the JMOL. You know, you can spin it around. David talked about some of the JMOL functionality we have integrated, the supercell. We can actually show some planes. some crystallographic paints, HKL. People are familiar with that. Oh, 1 second, it froze on me. Okay, so you can see that it pops up. We actually even have a way of loading up some of the symmetry operations. Okay, so I'm not gonna go into too much detail here, but you can actually see visualize how the symmetry operation looks like. Okay, so if you perform the symmetry operations a number of times, depending on the symmetry, you're actually going to return back the original orientation of the crystal. So people interested about learning about symmetry, there's a lot of things here. There's a lot of cool visualizations here for that. And then all of the relevant data, right? Symmetry, thermodynamic properties, the chemistry, magnetic properties, everything, a lot of different properties you can think of, they're here. Okay. So let's go back to the convex hull. So instead of the eye, let's click on selected hulls and give it a second. It's a little slow for me. My internet is also suffering from Zoom. So hold on. Oop, it froze. We're gonna go back. I'm gonna go back to it. Reload. 1 second. Okay. All right, let's click here. I'm gonna find my way back. Hopefully no one else is having trouble with this. That button should have gotten you directly to it. Okay. I'm gonna close this out. All right, so we're back to the convex hull. The other things I wanted to show you, some of the other, you can toggle points here. So you can, just look at the surface. You can highlight hull points. Okay, so that's going to it's going to highlight all the points here, and they're going to be shown here. You can click download PDF. There's 3 different formats you can get. There's the PDF, there's the tech, there's like sort of a plain text format, and then a JSON response, which is going to be very nice for integrating with Python. Okay, so I'm going to open up the PDF. Should be pretty quick for everybody. So here we have a nice PDF that you can download and take away with you. This is a nice working document, and I'll tell you what that means in a second. But here we have an illustration of the ternary hull. Again, the blue here is the blue versus orange is illustrating depth. Okay, so this is a 3D object, and you see all the facets here. And what do we have in the rest of the report? So we have 22 pages of document. So this is listing in arity. Okay, so this is first it lists the ternaries, and then if you scroll down, you'll see that the binaries come up next. Hold on. Ooh, it's a little slow for me. I'm going to open it up in my own. Yeah, okay, here we go. Okay, so we have, you see we have the ternaries first, then the, I think I already passed the binaries. Yes, we have binaries, and then finally at the bottom we have the unaries. Okay, unaries are all the way at the bottom. We have a lot of binaries. So here we have the unaries. So it's listed in chemical complexity order. So what do we have here? So we have the ternaries, and we see that the first system here is unstable. Okay, so it's going to be, it sits above the hull. If we click on this, this is actually going to open up the entry page. Okay, so that opens up the entry page for that system. We have some properties of that entry. We have the AFLOW unique identifier. We have the space group before and after relaxation, the spin, the enthalpy of formation. This is the entropic temperature. Professor Criterion talked about that earlier. And then we have the distance to the hull. Okay, so it's 162 MeV per atom above the hull. Because it's unstable, we also show the decomposition reaction, and it's balanced. Okay. Now, the second compound we have is a ground state system. Okay, and you can visually see that because I highlight them in green. Okay, so these are all of the compounds that have this ratio of components, but the green one is the one that sits on the hull, and these all reside above it. Okay, so these are all different polytopes of it. One second. One second. So we have, so the green here shows the one that is on the hull. And if you, I'll get to your question in 1 second. You can see here that for other ground state systems, we might have two compounds highlighted because that's because we did the symmetry, we did the analysis of the crystals, and we see that they are equivalent. Okay, and the orange tells us which structures are similar, and how we define similar by having the same space group relaxed. Okay. So what other properties do we show here? We also show the stability criterion. I'll define when we get back to the slides. And this is the n+1 energy that Professor Carrillo was talking about earlier. We also show the vertices of the facets. So these are systems that are in three-phase equilibria. Okay, so what does that mean? That means if we're looking at this particular compound here, the systems that are in three-phase equilibria are this system and this system. Okay, so they form the triangle that it sits on. Okay, so these are all systems that are in three-phase equilibria. These systems are also in three-phase equilibria. So are these systems, etc., etc. Okay, so that gives you the full list here. All right. So last thing I want to mention is this. I said this is a working document, because if you look, this is a point that you can click on. Okay, so that's going to take you to that point in the document. Okay, so here we have that point. You can look at the data. We have other links embedded in the document. You can click here, and you're going to go to that part of the document. Okay, so it really is a working document. Okay, so let me answer your question. How is formation enthalpy defined? Well, I defined it in one of the earlier slides. It was written at the bottom, but this is formation enthalpy. Okay, so formation enthalpy is, remember, we're looking at just enthalpy. And so the formation enthalpy is if I zero out the enthalpies of the individual components. Okay, so here is the equation for the formation enthalpy. It is the enthalpy of the compound, so this mixture here, minus the compositionally weighted enthalpies of the pure components. Okay, so that is how the formation enthalpy is defined. All right, so we're going to pick it up again with the slides. I was here. Okay, so we'll start from here. Absolutely. Okay, so in sort of the same spirit as the distance to the hull, we want to ask the question, how stable are points on the hull? Okay, so remember, I told you that this analysis was done at 0 temperature and 0 pressure. And so it's possible that when we go to room temperature that it is going to change. The energies of the system is going to change as we incorporate pressure. These points are all going to start to move around, and the convex hull is going to look differently. Maybe we'll have different points on the hull. It's also, you also have to realize that this is a particular sampling of the compositional space. Okay, so we haven't sampled every possible configuration, every possible composition, and so you know, that you can sample every possible or possible arrangement. But this is, you know, there's an infinite number of ways you can change the system and get a different energy. So the question here is, what is the likelihood that this point that sits on the hull is going to stay on the hull, given that we haven't sampled every possible configuration? Is it possible that there's a phase that we haven't yet explored that could change the shape of the convex hull so that this point is no longer on the hull? Okay, and so this is what we define the stability criterion. So what we did is, for this particular point here, palladium platinum 50-50 mixture, we remove the point from the hull. We calculate the pseudo hull, which is now the convex hull without that point. Okay, so I highlight the difference, the different facets with dotted lines. And now I find the distance to that pseudo hull from below. Okay, so that distance here, you can imagine that if the distance is very large, then it's going to be very difficult to find another point that's going to overcome that energy barrier to change the convex hull and remove that point from the hull. Okay, in this case, it's 6 MeV per atom, so it's not very large. But this is really a measure of how stable the point is on the hull. Okay. And I will answer your question just after I get to the next slide. So what is the point of the stability criterion? Okay, so is it useful? Well, we used it in a study that we did with a group led by Professor Sanvito in Dublin College, in Trinity College in Dublin. We looked for permanent magnets among the Heusler prototype. Okay, so David mentioned, I think he mentioned the Heusler prototype. This is there's 3 different variants here of structural arrangement of atoms. Okay, and we decorated these prototypes with 51 different metals. Okay, different elements from the periodic table to make 200,000 candidates. Okay, and so we wanted to filter through these possible candidates for systems that are going to be likely stable. Okay, so we want to look at ground state systems, those that are magnetic. Okay, and after doing some of these filtering criteria, we were still left with, I think the number was 22 different candidates. Okay, so what we did is to eliminate to systems that we thought were going to be really robustly stable thermodynamically, we looked for systems that had a stability criterion of at least 30 MeV. Okay, so above that room temperature energy that I talked about. And of those, there were 4 systems and 2 were formed. Okay, so I have the experimental data for one of those systems, cobalt, manganese, titanium system. Here I have the magnetization curve. You can see that it's ferromagnetic. And I have the Curie temperature here, which you can see it's about 950 Kelvin, which we actually predicted almost exactly. And we have the XRD data, which shows that it is indeed the Heusler FCC structure that we expect. And from the EDS data, we can see that it is a single phase material. Okay, you can see that everything is uniformly distributed. Okay, we've already done this. I'm not going to talk in great detail here because we don't have the command line, but I want to point out that you can do this analysis from your computer. Okay, the Convex Hall data is actually, if you run this, you can download and install AFLOW on your laptop, and if you have an internet connection, then if you run these commands, okay, the slide is here, so you can grab the slides later. You can actually run this analysis on your laptop and get back the PDFs. You can get back the JSON and all of that. And we also have a Python wrapper that's available. You can get that again through the AFLOW.org website. And because we have a Python wrapper, we also have a Jupyter Notebook wrapper. Okay, so for those of you that are familiar with Jupyter Notebooks, that there is the ability to create the notebook and to work with the notebook inside of Jupyter. So I'm going to take a second and answer some of the questions. The implication of the n+1 energy. Well, this is something that Professor Criterion covered in the lecture from this morning, but I guess I don't know if I have a good visualization for it, but the n+1 energy, what it's capturing is if we have this convex hull here, okay, and we want to know what the n+1 energy is. The n+1 energy for this system is, we look at the palladium platinum system and we remove all of the binaries. Okay, so if we remove all of the binaries from the system, we're just going to be left with, if you remember, I had a picture for this earlier. One second. We're just going to be left with this picture. Okay, so actually the n+1 energy for a binary compound is the same as the enthalpy of formation. Okay, now this is going to get more complicated as you go to ternary systems, because when you go to ternary systems, the n+1 energy for a ternary system is you remove all of the ternary compounds except for the compound you're looking at, and then look at the distance to the hull for the binaries and the ternaries included. Okay. And the physical implication of the n+1 energy, well, this is going to tell us what is the gain in ordering in terms of, okay, remember our goal here is to minimize the Gibbs free energy. So the n+1 energy is a good way of looking at the competition between the enthalpy and the entropy. Again, remember these two in the Gibbs free energy, these two components, they battle each other in terms of lowering the energy. So we want to look at the competition between the enthalpy gain. What is the enthalpy gain as we increase the number of species? Okay, he showed this very nice plot where you had the enthalpy gain, and then if you look at the entropy gain, as you increase the number of species, eventually entropy overtakes the enthalpy. Okay, so that's the physical implication. It's a nice descriptor for analyzing the competition between entropy and enthalpy as we increase the species count. Okay. The next question is there a pseudo phase diagram for different compounds, such as the BET? Well, I mean, you can make these phase diagrams, no problem. You can make these phase diagrams, and AFLOW will automatically create. It'll calculate the pseudo Hull to calculate the stability criterion. So yes, for any particular convex hull that you call with AFLOW, it will create in order to calculate the stability criterion, it will create the pseudo hull. I don't have an illustration. Well, this is the illustration here, but yes. So if you did the bismuth tellurium system, well, I guess you want it. I don't understand. Are you trying to do the bismuth tellurium, or are you trying to do antimony and selenium? Let me know if you want to write in the chat. You're welcome to unmic too if you want to ask the question.
My question is, pseudo phase means bismuth telluride is one phase and antimony selenide is another phase, and then they combine together to form a two binary phase diagram, like
right. So you're saying if I had this picture here, and I had on one side I had bismuth tellurium, and then I have antimony and selenium on this side, right? And then you want to look at all the compounds in between. So
yeah.
Yes. So you can pull that data and construct the convex hull. Right now, with the way that you interact with the convex hull, you cannot create that convex hull automatically with AFLOW. But we do have, you can look at the cross section of that data space and from let's say the AFLOW database and look at what the pseudo hull is for sure. That is something that generalizes in that respect. Absolutely.
Okay, thank you. So I wonder, could we find it like what we did from the AFLOW that you showed? We have 3 elements phase diagram. I wonder we can also find similar like phase diagram, like Schroeder phase diagram in AFLOW.
Similar phase diagrams to what?
Like pseudo phase diagram, like instead of just one element on each point, we have 2 or more than 2.
Well, no, but this is the pseudo phase diagram. I think we're confusing terms here. So what I called the pseudo hull here is just the hull without a particular point. I think what you mean by pseudo phase diagram is kind of a pseudo ternary, right? Where you're just looking at binaries. That functionality, like I said, that's not something that we have accessible through our module on the website. But if you wanted to construct the convex hull from data with the AFLOW database, that can certainly be done. But we don't have inputs for let's say for doing 2 components on this side and 2 components on this side. This is functionality that we need to add. But the data for that cross section does exist, and so we just need to create the functionality for that.
Gotcha. Thank you.
Absolutely. Okay. So I think that answers the question. Rico, how am I doing on time? I think I'm almost out of time, right?
Yeah, almost. But I guess you can you can do 2-3 more minutes if you like.
Sure. Okay. So I'm just gonna walk through the exercises with everybody. 1 second. So I just want to show you how you would do these exercises if you were to do them on your own. Okay. So let me see if I can get both of them up. We're gonna run through 1 or 2 of the exercises together. All right. So the first exercise is, what is the distance for Al17CO12 from the hull? Okay. So how would you go about doing this? So we go to if we go to the app, we go to AFLOW-CHULL, I'm going to type in ALCO, hit submit, and it's going to calculate. So give it a minute. Oh, and while I'm doing that, let me see if I can answer the question. Can AFLA predict about materials that are not present in the database? I have, and I want to form, yes, okay, so this is a question of how we, okay, well, your particular, this system is a disordered system. We do have a module for performing such calculations of disordered systems. I'll ask if one of my colleagues can put the DOI for that, because unfortunately, we don't have enough time to go through it today. We do have workshops online, presentations online that I do walk through the module. It's called AFLOW-CHULL for partial occupation. And so if somebody maybe puts the DOI for the paper and the presentation in the chat, I would appreciate it. But you see here that I just want to run really quickly through the first exercise. So I'm going to hit download PDF to answer this question, and it's going to open up. And so we want to look for AL17CO12. What is the distance to that to the hull? So we're going to scroll through the different compounds we have. I know it's a little small for you, but I'm going to try to zoom in. So AL17. Right here. Okay, so the system's right here. Here's the compound, and you can see that the distance to the hull is 243. Okay, so it's really high above the hull. It's very unstable. Okay, so the rest of the questions here, they're variants of downloading the PDF and looking up the data, but it looks like, okay, thank you. So you posted that up there. Okay. Are CHULL limited to ternaries? No, absolutely not. So CHULL can actually do any n dimensions, okay, as long as we have data, obviously, because as we increase the dimensionality, the computation power, it becomes more and more computationally difficult. So Professor Criterion presented today on 5-metal carbide, so that's a 6-dimensional system. So we do have, we have done convex hulls for 6-dimensional, we've created 6-dimensional polyhedra. Okay, so this cannot be visualized. We don't have the capacity to visualize in 3 dimensions, only projections, right? You can visualize projections of it, which would just be ternaries or binaries, whatever projection you want to take, but you can't visualize it, but the analysis can still be done and all of the properties can be taken. So AFLOW is n-dimensional in that respect. Okay, I want to see if there's any other questions I missed. I think that's everything. If anyone has any other questions, you're more than welcome to shoot me an email here. And with that, I'm going to wrap up my session and pass it over to Dr. Friedrich, who's going to present on a very important correction it's going to be very important for correcting the convex hull and the formation enthalpies in general for polar systems. So I hand it over to Dr. Friedrich now. Thank you, everybody.